All right, I think we can begin with the webinar. Hello and welcome everyone. Thank you for joining us today. My name is Adrian Kramer. I'm one of the application engineers at Diabatix. And in today's webinar, I will be covering LED thermal management and generative heatsink design. Our company, Diabatix, we specialize in all things conjugate heat transfer. So whether you need to perform a thermal analysis or you will want to be designing new cooling solutions from scratch, we have the answers to those needs. And of course, in the context of the LED and lighting industry, overheating is a constant problem that needs solving for. So I will show you how to use our software tool, ColdStream, to perform a thermal analysis, and then also how you can use generative design to create new heat sinks specifically for your LEDs and lighting fixtures. All right, to provide an agenda for what we will be covering today, first I will explain why thermal analysis is beneficial and needed. Secondly, I will discuss a thermal analysis use case, so with a particular lighting fixture in the LED industry. I will showcase how we did a CFD simulation to get some insights on the behavior, on the thermal behavior. And then I will introduce the concept of generative design to you and how ColdStream applies this for heat sinks in the LED industry. And then at the end, I can show you how you can already discover ColdStream today. And if there's some time at the end, we can have a Q&A session to address any questions you might have. So please feel free to post your questions in the chat. We also have some moderators following along, and they might get around to answering your questions even before the end of the webinar. So please don't be shy. All right. Well, why thermal analysis? Well, frankly, it saves you time and money. So harnessing the power of CFD-backed simulations to understand what is the thermal and what is the flow behavior of my lighting fixture, it helps you with shorter design cycles to market. So whether it is shortening the prototyping phase or allowing you to order the right parts, thermal analysis basically gives you an indication of how your product behaves in untested environment, and it can replace your experimental validation entirely. So if you're still using experimental setups to test prototypes, well, you should really consider introducing thermal analysis into your workflow, because simply you can get results faster than an experimental setup. You get more information than experimental tests, for example, on the flow behavior for the air volume around the heatsink or the LED. This would be very difficult to test using an experimental setup, and using CFD simulations, you can get some valuable insights on how the air behaves around it, but you can also follow how the heat dissipates throughout the part, and you can actually get measurements of the temperature, not just on the surface like you would measure in an experiment, but you can also see the temperature, for example, dissipating throughout the part itself. And in addition to the operational benefits of doing thermal analysis, you simply also get increased confidence in your product performance. So this allows you to do a smarter choice of heatsink, and you can also enjoy longer LED lifetimes, because you understand that at any given operation condition, your LED is staying within the operating temperatures that are desired. And like I already mentioned, you can also make sure that you're ordering the correct parts, that your part is operating at the temperature necessary, and just shortening the overall design cycle as such. All right, and with thermal analysis, it is also important because there are quite a few complex physical phenomena that need to be modeled. And so the three basic methods of heat transfer are conduction, convection, and radiation. And any good thermal analysis tool, any software-driven thermal analysis tool, will be able to model the effects of all three of these. And this is quite important because in the LED industry, any light fixture will have all three of those occurring in a very tight space around the fixture. So conduction is the most fundamental form of heat transfer. It is when different materials are in direct contact with each other, transferring energy, while convection is the transferring of energy through the motion of matter. So in the context of LEDs, this is typically via the air volume that is surrounding the light fixture. So whether that is natural convection or forced convection, all these things can be modeled in ColdStream. And then lastly, you have the effects of radiation, which is the transfer of energy through the help of electromagnetic waves. And this phenomena can also be modeled in ColdStream quite easily and conveniently. There are a couple more phenomena that are also very important to include. For one, buoyancy is quite important, especially with light fixtures. And buoyancy is essentially the fluid flow that occurs because of the difference in density due to a temperature gradient. So usually around a heatsink, the air particles that are closest to the hot heatsink, those will heat up, and due to a difference in density, they will rise, and therefore you have natural convection with some airflow around the heatsink due to the change in temperature. Secondly, turbulence can be modeled inside of ColdStream to have an appropriate representation of whether the airflow is laminar or turbulent. And then lastly, we can make sure that temperature-dependent properties are also incorporated as different material properties. And they can vary highly because of the dependency that they have on temperature. And to introduce thermal analysis to you, I will be using this light fixture as an example. So over on the left, you see an image of the actual light fixture, and on the right, you see the finished result showcasing a temperature gradient across the entire product. And so what was important to analyze in this scenario? Well, just picture the setting. You want to know how's your LED performing, or how's your light fixture performing with a certain heat output from your light sources at a certain operating condition. And you just want to know that quite fast without having to set up any experiments. Well, CFD simulations doing thermal analysis using CFD is your answer to that. And so in this case, this specific product has a temperature class of T5, and you might be familiar with this term. It essentially means that any material that stays below 100 degrees C does not have any risk of igniting. So we want to verify with the given output that we have, does our fixture stay below this hazardous temperature threshold. And so in a moment I will switch to our platform ColdStream, but before changing over to the software, I just want to showcase how convenient a case setup is. And so keep in mind, you really only have a few steps that you need to realize to be able to do such a thermal simulation. So first, you need to upload a geometry. So in this case, a CAD file of the lighting fixture. So ColdStream always adopts to the light fixture that you're trying to analyze. As long as you have a CAD file as input information, you can be doing thermal analysis. Secondly, you have to define your solids and your fluids. So any material definition or is it an air volume around the light fixture, those need to be specified. You set certain boundary conditions for the thermal and the flow behavior, and you can already download your results or visualize them conveniently in the post-processing options that are available on ColdStream. All right, I shall be switching over to ColdStream now. All right, you should now be able to see ColdStream. So I already done the first step that you need to start a case setup in ColdStream, that is uploading the geometry. So actually what you can see here is our light fixture that I just explained, modeled in a CAD environment and then uploaded to ColdStream. And so what we will do now is a full case setup, start to finish, show you how easy that is. And really to start this off, we want to define all the solids and fluids in the regions tree. So the first one being the LED lights. So you can see the LED lights, they sit in an array as such. And so to define them properly, you simply select to be a solid. And then you have to choose which material it's made out of. So this will be the main input for all of our solids. And so we have this gallium arsenide right here. And then additionally for our LED lights, what's also very important is that we model the effects of radiation, and these can be simply modeled through just clicking one button. Additionally, the LED lights are also our main heat source in the entire fixture. So to introduce a heat source, you would add heat source here, and this one is 142.5, which is then dissipated across all of them. So over the entire volume of all of these LED lights dissipated equally. So to define the remaining solids, let's take this LED light fixing plate next. And we will simply here choose an aluminum. All right. And the remainder of the settings are not necessary for the fixing plate. And the glass is on this side. And so to model the glass, we would pick the material. So for example, this is silica glass. And in this case, we also want to enable the effects of radiation as the majority of the heat dissipates through the glass. And then the remaining parts are simply the housing front. So let's select that as a solid. And this can simply be in aluminum. So quite basic definition. And then this solid, okay, that's actually the fixture that connects it to the wall. So see, this can be defined better. So let's take that opportunity and define this as a wall fixture. And then we will also select again the same aluminum. And so ColdStream comes with a set of predefined materials in our library, but if you want to add your own custom one, it's as easy as filling out this data sheet, and then it's always readily available in your library. And so the last one is the heatsink we see in the back, and that was also simply aluminum. All right, and then we have already defined all of our solids, and we've actually already defined our thermal boundary condition as well with setting this LED light. So what's left to do is defining the fluid, which is our big air box right here. And then the boundary conditions for that flow. So let's select the fluid. We can of course rename this as air, and then select the material as such. So whether it's air cooled, liquid cooled, doesn't matter. ColdStream will adapt to your situation. Of course, for LEDs, the majority of those will be air cooled. Then we want to model the effects of buoyancy. So again, you just have to check one box to include that. And what's important here is the gravitation vector. And so you can check that orientation. If we look at the fixture again, All right, this yellow axis is Y. You get the confirmation down here. So we would like to enable negative Y as our gravitation vector. Here you introduce the turbulence model. In this scenario, K omega SST will work just fine for our air volume. And then we also want to enable the effects of radiation for our air volume. Great, so our main fluid is defined. Now just the boundary conditions are left. And so in ColdStream, how we define the boundary conditions for flow is through using surface patches for every side of the air box. And so in this case, we will have pressure inlets on all the sides and the bottom, and a pressure outlet on the top. So I'll start defining that. And for the pressure inlet, in this case for natural convection, we have operating conditions of 298 Kelvin. And for natural convection, we simply want a pressure of 0. So I now have to do this for all of the sides. This I see is the top. So in this instance, it would be our pressure outlet. And that one's even easier to define because it simply needs to be a pressure of 0. And for pressure outlets, this will always be the case, even if you have, for example, forced flow. But with natural convection, it will always be 0 pascals for either inlet or outlet. So just to finish this up, let me define all of these, and then just to do that 3 more times, and then the case is finished. All right. Now the bottom as a pressure inlet. What you could also define is a fixed flow rate inlet, or using fans and pumps, but of course that would make it forced convection. However, again, in ColdStream will adapt to your scenario, so maybe you're using a fan to cool down your lighting fixture, but in this instance it was not needed. All right, and now you have this great visual cue over here with the green check marks that all regions and subregions and boundary patches are properly defined, and maybe you notice that the submit button is now blue instead of grayed out, which allows you to submit this as a CFD simulation. So you see, you don't need to be a CFD expert to use ColdStream to do thermal analysis and management, because we remove any need or user input for meshing. Our program uses an intelligent meshing automation that meshes the entire volume accordingly to give you robust, accurate examples. Now we would like to look at the results of the simulation that we just ran. So I switched over to the results view, and as you can see, we have the exact same light fixture here. And what might be interesting to look at is, for example, the flow behavior of our air volume. So to look at that, we can enable the streamlines here, and we would want to hide other things. So you can see how the flow behaves as it's cooling the entire light fixture. And so I think what's also important or interesting to see is how does the heatsink actually behave temperature-wise as the air is cooling it. So you can include a temperature gradient for a nice visualization of the heatsink itself. Of course, the hotspots created by the LED lights are very visible, and we can see that our T max is around 70 degrees Celsius, so well below that hazardous operating or hazardous temperature limit at 100 degrees C, since this is a T5 class light fixture. So that's one of the good options. What we could, for example, also look at is a sliced view of the air. So let me just enable only this. And here we could, for example, see then how does the temperature rise from the heat source. So In my opinion, this is a very nice visual representation of the heat leaving the heatsink as the hot air through buoyancy is rising. You could also look at the streamlines there. So there you can actually see how the velocity of the air is increasing due to the due to it being heated up. And so in ColdStream you can actually take screenshots of all of these. So you have very convenient post-processing, and in case you would like to, for example, showcase this in an internal report. So all of those things are readily available in this 3D results viewer. In addition to that, we also have a tabular overview, which is also quite nice. So here, for example, you have the Tmax, Tmean, and Tmin. Again, seeing, okay, the Tmax, okay, actually at the LED light, it's 71.65, but again, it's staying underneath that 100 degrees C threshold. So we actually proved what we wanted to showcase, and that is that given at the operating condition, what are my temperatures? Am I staying within the allowable range? Which was the case here. Another nice thing is our thermal network. So any ColdStream simulation will have one of these. And this might also be new to you, but essentially a thermal network gives you a nice visual cue of how the heat sources are connected to the other regions through their interfaces, and you can track how the heat is removed as it dissipates through the part. So for example, on the LED light, you can see the temperature in the source, and then if we follow that, for example, to the heat sink right here, you can then see how has the temperature decreased, and of course from the heat sink it then moves to the fluid region. So this is also a nice visual overview, especially if you have a lot of different parts. This can help with keeping track of that. Another thing that could be very convenient is if you're, for example, comparing two different simulations. So say you want to see what does or how is the behavior different at different operating conditions. You actually can add, well, I should start from scratch. So we have a compare cases view. And if you would like to, for example, compare this operating condition with another one, you can add several cases to a comparative view. So say you want to investigate different temperature points, you can then see that in a nice tabular overview comparing one to the other. Say, for example, you're comparing different heat sources, different strengths of LEDs, and you want to see at what point do I reach a critical temperature. You could do that very conveniently with simulating all of that in parallel and then seeing the results in this section here. All right, and that is essentially how you do a thermal analysis for proper thermal management in ColdStream. So I shall switch back to my slides now. All right, and now starting the second half of the webinar, I will now be introducing the concept of generative heatsink design to you. And what I've prepared for that is essentially a video, because I think this explains it way faster and you actually see it in action. So in this case, it is a heatsink for a PCB board, but the concept remains the same, that for any heatsink that you need to construct around a light or an LED, we would apply the same principles. So you see the heat sources are located on the bottom, and already you see ColdStream in action doing its generative design for conjugate heat transfer. And what's novel about ColdStream is that it combines both flow and thermal boundary conditions into one subset and does topology optimization to address the needs for both of those requirements. And so here you can see quite nicely one a quite final iteration of a heatsink that you can expect when you use ColdStream for generative design. All right, and so how using ColdStream for generative design differs from the thermal analysis that I just showed you is essentially there's only one new thing. It is the design space that you have to define. And so essentially, in addition to the air volume that you model, you also have to include a subregion that defines the design freedom that ColdStream has to decide, would I like to place structures or not? And then when you submit the case, ColdStream, as you saw in the video, will compare hundreds of different designs to each other, each one of those backed with a CFD performance evaluation, so a full simulation like we saw with the LED fixture I just showed you, and eventually reach a global optimum of the best performing design. So you just have to specify where do I have space for the heatsink, and ColdStream will find the most optimal one, like you see right here. And so for context, this was a LED fixture that had LED strips on 3 sides, and therefore you see the design as such. All right, and then switching to this view, we actually modeled 3 different ones, and so you can see them here. This was the one from the render with heat sources on 3 sides. Over here you see one with 4 sides, and the top one right here, this one is actually a liquid cooled design. We also wanted to showcase how do the structures different if we're using a different fluid medium. And actually what I have with me today is I have all of these printed out. So ColdStream actually guarantees fully manufacturable designs. You can see here all the different designs that were created. Here's the 4th one. And so what's interesting is that, of course, ColdStream only generated structures right here and on the sides because the case setup dictated it. So we had heat sources on 3 sides, while this one ended up being a symmetrical design because we had heat sources on all 4 sides of it. And so that really shows how generative design adapts to the needs that you have. So if, for example, you have very limited design freedom because you work in a tight packaging space, or there's simply not a lot of room in the ceiling that you're attaching your fixture in, you should really consider generative design because it gets the most out of the performance. All right, and then moving on. So to summarize the possibilities that you have with ColdStream, well, you can do very easy thermal analysis without being a CFD expert. You have convenient post-processing options readily available to you. As soon as the case is done, you will get a notification and you can investigate this from anywhere. Since we are a cloud-based software, it is not just a software that you download on one machine, but rather as long as you have a browser, you can access ColdStream. And in addition, for generative design, the entry barrier to harness such powerful structure creating technology, it's actually quite low. So you could already today be designing your heat sinks with generative design now, thanks to ColdStream. All right, now I see we have a little more time left. So maybe this is a good time to address some questions that people may have had in the chat. So all right, taking the first question here, it is you showed a case setup for a naturally convection case. Can I also do this if I have a fan helping to cool my heatsink? Yes, indeed. So to switch from natural to forced convection, it is actually quite convenient. You just have to adjust the boundary conditions slightly So in the example that I gave, I implemented pressure inlets. For a forced convection case setup, you can either use a fixed flow rate inlet or a fan inlet. And so you can actually model your specific fans directly in ColdStream, and those will also be part of your library. So that is readily available right now on ColdStream. All right, maybe another question. Yes, someone said your designs look very much inspired by things we can see in nature, for example, like a snowflake. Did you train your solver with existing designs and examples? So yeah, actually, I agree. This one does really look like a snowflake pattern. But to be honest, our approach, it doesn't have a database of existing solutions attached to it, but rather it is really doing topology optimization from scratch. So that includes doing a finite volume analysis and solving the Navier-Stokes equations in a gradient-based approach. So yeah, that's really what ColdStream does in the back end. But yeah, there's no subset of existing solutions that we select from, but rather each geometry will be unique to your case setup. All right, someone asked, I was wondering about the manufacturability of your designs. You showed the ones that you had printed out. Can you explain how they were manufactured? And can I do it if I would want to use die casting? Yeah, great question. So actually these that I was showing you, so these were just manufactured with an extrusion manufacturing technique, but absolutely in ColdStream there are several different manufacturing techniques which you impose as a constraint on your design region, and die casting is readily available on ColdStream as well. So it's not a problem at all, and your solution will be unique to the manufacturing technique that you impose. So for example, we have 3D printing as well. That of course gives quite a lot of design freedom, but you can always select which technique your preference is in ColdStream. All right, well, that concludes our time and questions. What I want to leave you with is how you can discover ColdStream yourself. Actually, right now, you could have a ColdStream Try Now account. It is essentially a viewer account where you can see some predefined cases from ourselves, including the thermal simulation that I showed you today. And you can already get a feel for how thermal analysis and post-processing can be done in ColdStream, but also some more examples of generative design than the ones that I showed you today. And then lastly, of course, feel free to shoot me any questions you might have, or if you want to learn more, if you would like to have resources on certain topics, please don't hesitate to stay in touch with us. My contact information can be seen down below. All right, well, thank you all for joining. I hope you learned a thing or two. And like I said, if you would like to stay in touch with us, please don't hesitate to reach out. Thank you so much for watching, and have a good rest of your day. Goodbye.